Okay, as I said, I'm going to work beginning with these problems. I'm going to work the problems in chapter 15 in lieu of the lectures. So from chapter 15 on, for the rest of the year, we will not be turning in our homework. We will just be doing the grades based on the quizzes and tests, but not the homework. Also, from time to time, there may be some hesitation as I do a calculation or something, so I'll do my best to try to minimize those sorts of things, but there may be a little bit of jerkiness. So today we're going to be working on this group of problems, and you can see the first two are problem 2 and 8, on page 816, and I have this out already. So let's take a look at problem number 2 first. It says, complete the change in concentration for each of the following reactions. So the first one, we have barium sulfate, solid, that decomposes or ionizes to barium ion plus sulfate ion. And if we designate this as X, then this line that's left would also have to be X, since both of these have 1 as a coefficient. Now, if we had a concentration over here, say 0.1, then it would be minus X for this. B is silver sulfate, solid, ionizes to form 2 silver ions and 1 sulfate ion. And the concentration here, if we designate the sulfate as X, that means that this has to be 2X. And again, if this were a concentration, say 0.1, it would be 0.1 minus X. C is aluminum hydroxide solid, which looks like this. It ionizes to form aluminum ions plus 3 hydroxide ions. And if we designate again aluminum as X, then this would have to be 3X. I wrote 2, but there it is, 3X. D is lead hydroxychloride solid. Hydroxychloride solid forms a lead ion, which is 2 plus a hydroxide ion plus a chloride ion. And if the hydroxide ion is X, then both the lead and the hydroxide ion or chloride ions are also X. The last one, E, is calcium acetate. I don't know exactly how to say this. This is arsenate is what it is. Solid. Decomposes to form 3 calcium ions plus 2 arsenate ions. And if the calcium is 3X, then this is 2X. So that's problem number 2. Fairly simple and straightforward. Let's move on to problem number 8. Problem number 8 says, write the ionic equation for the dissolution and the solubility product, KSP expression, for each of the following slightly solid ionic compounds. Now when it says slightly soluble, that means that the reactant is primarily a solid and cannot be expressed as a concentration, which is why it is not included in the KSP. When you have a solid, in any situation, when you have a solid, that solid cannot be expressed as a concentration and therefore is not part of the equilibrium calculation. The first is lead chloride. It decomposes to form lead plus 2 Cl minus. So the KSP for this would be lead concentration, ion concentration, times the chloride ion concentration squared. Squared because the coefficient is 2 here. B is silver sulfide. Silver sulfide decomposes to form 2 silver ions plus a sulfide ion. The KSP is expressed as silver ion concentration squared times the sulfide ion concentration. The third one is whatever SR is. I don't know what that is right off the top of my head. So SR3 PO4 phosphate, strontium phosphate, goes to form 3 strontium ions plus 2 phosphate ions. And the KSP for that is going to be equal to the strontium ion concentration cubed plus, or times, the phosphate ion concentration squared. And the last one here is strontium sulfate. Not sure why they have such a thing for strontium, but there it is. So that's Sr2 plus SO4 2 minus. So the KSP is going to be Sr2 plus times SO4 2 minus. So that is the homework for the first day. Let's move over and see what's next. We got 10, 13, and 24. So if we go to 10, the Handbook of Chemistry and Physics, blah, 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 gives solubilities for the following compounds in grams per 100 milliliters of water. Because these compounds are only slightly soluble, assume the volume does not change on dissolution and calculate the solubility product for each. Okay, the reason they said that last part is because remember that molarity, which is a concentration, is based on a liter of solution. So each of these, it says solubility per 100 milliliters, so you multiply it by 10. So you have BaSiF6, BaSiF6, and that has a concentrate or a solubility, according to this, of 0.026 grams per 100 milliliters of fluid. And they tell you that this is a single ion, so that this dissolution looks like this. You have Ba2 plus SiF6 2 minus. Okay, so what this tells you is you have this many grams. So what you have to calculate next is the molecular weight for this. And if you look up each of these, barium is 137.3, Silicon is 28.09. And F, fluorine, is 19. And that's going to be times 6. So the molecular weight here is 279.39. If we take this number right here and divide that by 279.39, we end up with 9.3 times 10 to the minus 5, and that's moles per 100. So per liter, that would be times 10 to the minus 6. So let's just go ahead and put that minus 6 in here. Moles per liter. So that means that you have this many moles of per liter of this. So you have this many moles per liter of this, and this many moles per liter of this. So the KSP here would be Ba2 plus times SiF6 2 minus. So that's going to equal the 9.3 times 10 to the minus 6 basically squared. Which is 8.7 times 10 to the minus 12. Well, 11 actually. Because 9 squared is 81, so it's 10 to the minus 11, keeping the exponents correct. The next one is, I don't know why they have such simple compounds. Makes it easy. CeIO3 to the 4th. And what that would be is, that would break down to form Ce4 plus 4IO3 minus, and the KSP is going to equal Ce4 plus times IO3 minus to the 4th power. The amount in grams is 1.5 times 10 to the minus 2 grams per 100. Actually, if this many grams per 100, then it's I think I may have miscalculated this here. I think this may be, instead of, this should be minus 5, and that's grams per, or moles per 100, so it would be 10 to the minus 4 moles per liter. So I think my number over here should be minus 4, and that this should be minus 7. Because it's 1.5 times 10 to the 2 grams per 100 milliliters, which means you're going to have 1.5 times 10 to the minus 1 grams per liter. And then you're going to use that to make your calculation. CE is 140. I is 126.9. O is 16. The molecular weight for this right here is 839.6. So this is 0. Well, let's use exponentials. 1.7 times or 1.8 times 10 to the minus 4 moles per liter. Yeah, this is definitely the way it should be up here. I did this wrong the first time. So now we're going to take this and put it into this equation. 1.8 times 10 to the minus 4. And 4 times that. Remember, you have to multiply that by 4. So 1.8 times 4 is 7.2 times 10 to the minus 4 to the 4th power. So it's 4.7 times 10 to the minus 17. C. Gadolinium 2 sulfate. So this is going to break down to 2 gadolinium plus 3 sulfate. So the KSP is going to be gadolinium concentration squared times the sulfate concentration cubed. And the solubility is 3.98 grams per 100, which is 39.8 grams per liter. This is 69.7, and take my word for it, sulfate is 96. It's 4 times 16 is 64, plus 32 is 96. So this is 427.4 grams per mole. This concentration is 0.0931 moles per liter. So we put 2 times that for gadolinium, which is 0.186, and it'll be 3 times that for the sulfate, which is 0.279 cubed. So that cubed 0.0218, and this squared is 0.0346. So the KSP is going to be 7.54 times 10 to the minus 4. The last one, D, is ammonium platinum bromide, with the platinum bromide ion being the simple ion. So it's ammonium and then this platinum bromide is a single ion. So it looks like this. Plus, and the platinum bromide minus. So the KSP is going to be the ammonium concentration squared times the platinum bromide concentration, and the molecular weight here will be as follows. First of all, the amount of grams is 0.59 grams per 100, which is 5.9 grams per liter. Platinum is 195.1. Bromium is 79.9. This is 14 and this is 1. So if you take 14 times, or 1 times 4 is 4. So this whole thing together is 18. The molecular weight here is 710.5. So the concentration is 8.3 times 10 to the minus 3. So we put 2 times that in this slot. So that's going to be 1.66 times 10 to the minus 2 squared times 8.3 times 10 to the minus 3. So it's 2.3 times 10 to the minus 6.